Next speaker is Mr. Simon Ho from National Tsinghua University. He's talking about highly quasar host galaxies detected with hyperspectrum conf. Okay, please go ahead.
Hi, I'm Simon. My supervisor is Professor Tomo Goto. And today I want to talk about a topic which is unveiling quasar host galaxy and their Lyman alpha emission at redshift 6 by SHELLQs data. And last year, actually, I joined NEP conference too, and I was talking about NEP velocity. So this time I don't want to talk about the same thing, and so I talk about some new things. If you want to know about NEP velocity, please refer to a paper which was accepted 2 weeks ago, Ho et al. 2020. So let's start this talk. So to begin with, I want to tell you some basic terminologies which I mentioned. The first one is quasar, and the second one is host galaxy. So a quasar is an extremely luminous active galactic nucleus, and most astronomers believe that every quasar is powered by a supermassive black hole. And they also have concluded that most, if not all, galaxies host massive black holes at their centers. So here I show you a quasar. In the left panel, you can see a very bright quasar, which is 3C273. And at the right panel, you can see if we put a corona graph on it, the bright emission from the quasar is blocked. And you can see there is something around the quasar, which is actually the host galaxy. So actually, there are many astronomers studying the relationship between quasar and its host galaxy, like Milano et al. And C. Fernandez et al. They found that numerous AGN show evidence of starburst features. And for Genzo et al. And Goto et al., they found that half of the ULERGs contain simultaneously an AGN and starburst activity. So why is this relationship between a quasar and its host galaxy so important that they want to study about it? It's because this kind of relationship provides us the clues for the study of the formation processes of galaxies and their central massive black holes. So I Googled about the studies of quasar's host galaxy at different C, and I found that there are studies about quasar host galaxy using super HSC camera at low C, which is as low as smaller than 1, and also multicolor imaging of redshift 2 quasar hosts, and ALMA observation of redshift 4.8, and even CO line emission at redshift 6. So far you see those quasar which is only detected within redshift 6. How about redshift which is higher than 6? So far I didn't find much paper about redshift which is higher than 6 because it is so difficult. And that is even more difficult for optical observation. And so far I've only found one paper about optical detection of higher than redshift 6 quasar host galaxy, which is by Goto et al. So in this paper they detected host galaxy around a quasar which is at redshift 6.43, and they also found a Lyman emission from it. So you may ask that why is it so difficult to find quasar host galaxy for quasar which is higher than redshift 6? I may show you a metaphor to explain how difficult this is. So there is an old Chinese saying that this one is the saying. So what does it mean? It means when girls pursue boys, they are separated by a piece of muslin. This is muslin. So when boys pursue girls, they are separated by a mountain. So you can know that when boys trying to find girlfriends, it's very difficult because they are separated by a mountain. So in our cases, this is me here, and I'm an astronomer. unfortunately, I'm not looking for girlfriends, but I'm looking for high redshift host galaxy. And between us, there is a big mountain, Oyama here. And so you can see that it's very difficult to find this thing because we are separated far away. And actually, in this case, the big mountain is the intergalactic medium, IgM. So to be more scientific, I can show you this graph here. So you can see that there are the 3 lines here. The red one is the high redshift, which is higher than 6. Redshift 6 quasar is line emission. You can see that it's very huge compared with the very small guy here, which is the redshift 6 galaxy. So you can see that the line emission, the difference between line emission from quasar and host galaxy is very huge. And it's very difficult to discover this very small guy. So what we have to do is we use stacking to increase the signal to noise ratio of that redshift 6 quasar. Let's say we have 15 images, so we can increase the signal to, we can increase the magnitude of the depth up to 2.12 magnitude. For example, for HCC C-band depth, originally it was like 25.9 magnitude. If we use stacking, we can increase it to 28 magnitude. And here I can show you that typical galaxies around quasar field in C-band is about 26.5 magnitude by ultrasound. So you can see that in this case, C-band magnitude from HSC is good enough if we use stacking to detect typical galaxy at redshift 6. So I want to present how I did the analysis by beginning with the sample and sample selection. The quasar sample we are using is mainly from the Subaru high-C exploration of low luminosity quasar, which is also known as SHELLQs. And we have also, our quasar are also identified by SDSS and CFHT-QS. In total, we have about 93 quasar samples. And we get a C-band and Y-band data from HSE SSP survey. So why did we use C-band and Y-band data only? Here I show you the emission lines of redshift 6 quasar and host galaxy. You can see that for the emission here, it is only covered by HSE C-band and Y-band. For those wavelength which is shorter than HSE C-band, we cannot detect anything. That's why we are only focusing on HSE C-band and HSE Y-band. So the first thing we did is we try to do quasar sample selection by removing quasar with nearby sources within 20 pixels so that there is no contamination while stacking. And also we remove sources with best seeing size that is over the 3 sigma distribution. I will talk about this later. And we also apply a redshift cut to remove non-detection in some bands. For example, like 6.8 for C-band. So what I'm saying that is, you can see here, these are the different line emission of different redshift quasar. If we put HSE C-band filter edge here, you can see that we can only detect line emission up to about 6.8. So we need to throw away, which is about redshift 6.8, because we cannot detect anything by using HSE C-band. That's why we use that criteria to remove those quasars. And also we have different seeing size in different images. And different seeing size is bad when we are doing stacking because we don't want them to be varied. So we try to unify the seeing size. Here I show you the seeing size distribution histogram in C-band of our quasar. And we plot a 3 sigma here. And actually we flow away those very bad seeing size. And we try to use Gaussian convolution to unify this seeing size to about the highest seeing size here, which is about 4.4. So we have about 46 quasars with seeing size 4.4 now. Yeah, after applying the above selection criteria, we are left with a sample of 46 clean quasars with a Seeing size of 4.4, and the redshift median is 6.13. And the next thing we want to do is we want to make a PSF, which is point spread function. We use S extractor by this paper, and we carefully pick 46 nearby stars from each of the quasar frame within 60 arcseconds. And we try to normalize the star images to flux 1 so that it's easier for stacking. And then finally we stack the stars with median as combined operation. Here I show you schematic images of how I do the analysis. So first we have 46 quasar images, and we do Gaussian convolution to unify Seeing size. And then there are 2 ways. Here we use the stars to stack it and then make this PSF. And then we do Gaussian PSF subtraction. So first thing we do is PSF subtraction. So in principle, for quasar with host galaxy, if we minus a PSF here, it should be left with only galaxy. So in our case, this is our result. You can see that there is a little bit surrounding around the quasar here, which is in our residue. And if we show you the radial profile of this PSF subtraction, you can see that there is an excess between the PSF plus sky and the quasar host. So actually we have detected an extended structure at for about 8.75 pixels, and the half-life radius is 1.49 arcsecond and corresponding to 9.3 kiloparsec. And the next thing we did is PSF plus static subtraction. So here again, in principle, if a quasar host is minus by a quasar host, there will be nothing left. So here again, we show you again, you can see that that surrounding white part is disappeared. So that is totally subtracted in this time. And again, I show you the radial profile. You can see that there is no more excess in this part. And so far, this is our result, and we have some more things to do in the future, which is like PSF subtraction in wideband, so that we can check that if the extended structure includes lambda alpha or not. And also, we want to do SED fitting with wideband and C-band images. So this is our summary, and I will leave the summary to you. Thank you.
Thank you very much for a nice talk. So, is any questions? I don't see question in Slack at the moment. Do you have questions? Because I am one of collaborators, so it's weird if I ask something, but
okay, then.
me.
So why redshift 6? Because as you say, low redshift is also unexplored, right, for quasars.
So actually, low redshift is more explored. I want to say.
More explored because you showed only a few papers, but you found a lot of papers.
Yeah, actually, lots of papers. But redshift 6 is not many. Very few.
Okay. Yeah.
Actually, if we really detect it, it's the first time ever. Or higher than redshift 6.
Okay.
Okay. So
Can I
one
ask a question. This is Myung-Shin.
Yes.
Okay. Thank you.
So if the host galaxy and the platform acceleration had followed the local relation, would you have this detected much stronger signal?
Strongest signal.
So what you are finding is kind of very faint structure, right?
Yes.
Is this something that you were expecting to find, or you could have found something more prominent if the local relation was just not evolving? The local relation for the host galaxy and that correlation was not evolving.
Yeah, I think we require future work to do that. And actually, we are expecting to find a host galaxy because we did a calculation. If we stack it, it should be able to detect it. Yeah. If not, there must be something wrong in our analysis. So.
Okay.
Okay, thank you very much. Final question is from Darijo Santos. How do we identify the identity of this extended structure? If this is a host galaxy or not? How do we identify? How do we know?
To identify.
Mm-hmm.
What I did a PSF subtraction and SHELLQs subtraction. So for a SHELLQs subtraction, the reason why I'm doing that is try to fit in with a galaxy profile to see if this is galaxy. If it's successfully fitted with SHELLQs, it's more likely to be a galaxy. But if you want to know if it's Lyman alpha emission, you also need to use like wideband detection to do it. So maybe in the future we'll do it to see how many percentage is Lyman alpha emission and how many percentage is galaxy. This is what we want to do.
Thank you very much. I think it's a good answer. Okay, let's thank speaker again. So.